All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Shana Ghadar. She is a senior machine learning manager at Adobe. Please join me in welcoming Shana to our virtual stage.
Good morning, everyone. My name is Shana, and today I'm going to present the applications of computer vision in industry. So I'm going to be covering different industries such as autonomous driving or e-commerce. I'm choosing these applications because of personal experience through various companies in the industry. All right, so here's the outline of my presentation. First, I'm going to talk about the basics of autonomous driving and how one can go about designing one car that can do driving without a driver. Then I'm going to switch to visual search and its applications in stock photography and e-commerce. And last but not least, I'm going to talk about ethical AI and why we should all take this seriously for the sake of humanity. Okay. The first one is autonomous driving. How do we design an autonomous car? The slide that you see here is a typical self-driving car. It has several sensors. How do we humans drive? We use our eyes to see and our ears to hear, but how does the car see? So we can use cameras for the car to see everywhere. Cameras are cheap sensors, so we can put them everywhere. And you can see in this picture, there are several cameras. The cameras are the gray ones, and you can put them all around the car. You can put them to detect traffic signs, to detect humans, to detect all the surround views, basically a digital side view mirror, or in the rear of your car. I mean, a lot of our cars today have backup cameras when we're trying to go backwards. The other sensor that we're using today in most of the cars are radars. Radars are also very cheap, and then you can put them all around the car. And we can have bunch of radars, one short range and long range radars. And today in most cars, we have long range radars for emergency braking and adaptive cruise control, which a lot of cars that are not autonomous yet are still offering. And the last sensor that many of autonomous cars have are LiDARs. LiDARs are a sensor based on laser, and they are very expensive. So some of the self-driving companies are announcing that they might design a self-driving car without the LiDAR, but many of them still do. LiDARs are very accurate, and they can map the environment for you. Okay, so this was a picture of a typical self-driving car. Now that we have a car with a lot of sensors, how do we go about designing a pipeline that gets us to autonomous driving? Okay, so we start with the sensor data, which can come from cameras, LiDARs, radars, everything. Using that sensor data, we now should understand what is around the car. Are there cars? Are there bikes? Are there pedestrians? What are the road signs? Where we are in the driving lane? Which lane lines are there? Having this, we now have to do behavior prediction. Why do we have to do behavior prediction? Because imagine you're driving in a highway in one lane, and then the car around you is trying to pass you or trying to come into your lane. So in addition to knowing that there's a car around you, you need to know that this car is going to come to your lane. So you take the proper actions. All right, so we now have the behavior predictions of around us. Having this, the car can now do trajectory planning. We need to know where we want to go. So we do this planning, and this planning talks to the car's controllers. And this one talks to the steering angle and the brakes and everything. Having that, now the car can take an action. It can take right or left, or it can brake or speed up. In this presentation, mostly I'm going to talk about the second bullet that you see here, the car surrounding, and how computer vision can be used for that. All right. So as I mentioned before, we humans use our eyes to see around the car, and it can translate very well to driverless cars as well. What do? We use cameras to see everything. Okay, so we put cameras all around the cars, but now what? What does this camera need to do? Well, the first thing, we need to detect what's around us. So we need to detect the objects. We need to detect most of the objects that are on the road, like cars, bikes, people, traffic light, traffic signs, and all of that. Now here, if we only had just one camera, most likely we could have just done 2D object detection. And by 2D object detection, I mean bounding box detection. But now, because we have several cameras, we can take advantage of the relationship of these cameras together and do a 3D object detection instead of a 2D. And what does a 3D object detection gives us? The depth of the object ahead of us. Regardless, doing just the object detection is not enough, right? We understand that there's cars and humans and bikes around us, but where are they? Are they 100 meters away, or are they just nearby? So we need to do depth estimation as well. And this is an example of a depth estimation deep learning model using just the mono camera. And this is the depth map that you see. So having this depth map, we can now infer what is the distance of the objects around us. Note that if we do the depth detection using just one camera, it won't be accurate. And also, it always depends on the scale. So the depth camera, the depth from a mono camera gives you a depth without units. So for example, you know that the car ahead of you is 6 units ahead of you, but you don't really know that unit. You need some ground truth to know what this unit is. But luckily, in self-driving cars, we have other cameras that we know their positions. We have other sensors that can give us the ground truth. So this getting the depth is much easier. All right. What else we do while we're driving? We need to know where we are, right? So we need to detect lane lines. This is the example that you see here is also a lane line detection method. Most of the time, we can detect lane lines as a linear module, which is basically this one, AX plus B, or a second order model or third order model. And this is the second order model, which can detect the curves. All of these images that you see here have been derived using deep learning. And I'm guessing all of you must have heard about deep learning. Basically, it's deep neural networks that can predict many things. And these days, most of the computer vision algorithms that you see are using deep learnings one way or another. All right, so now that we detect pretty much everything around us, what else is left? As I said before, we need to know what the objects are. And one thing that we can do tracking of the objects. We need to know where they are. For example, you see you are standing somewhere, the car is standing somewhere, and then there are some pedestrians. We need to know either they're crossing or they're just taking their own way and is not in our trajectory. So we need to do tracking. This is an example of a recent deep learning based tracking that is very fast and real time. And it uses bounding boxes to track people. So 2D bounding box detection is kind of necessary. What else? We've detected lane lines, but is that enough? Probably not. Imagine that you have an emergency vehicle driving behind you and you need to pull over somewhere, right? You need to know where are the spaces that you can park. And we usually, as humans, we can detect these things, but the car needs to know. So we can do free space detections as well. And the examples that you hear, these are the free space detected by a Tesla car. All right. So here's a question for you. Are bounding boxes enough for tracking? Maybe, maybe not. Imagine that 2 people or a bunch of objects, cars, are driving like very close to each other. The bounding boxes should be overlapping very much, right? So then it'll become very hard to detect which one is going somewhere, like the first one is going this way or the other one. So one way to mitigate that solution is to use instance segmentation instead of bounding boxes. And what is instance segmentation? Instance segmentation is semantic segmentation, basically pixel level segmentation, and you see here, but Also knowing that in addition to knowing the class of the object, you will know that this is like person 1, person 2, person 3, and person 4. And this will give us a lot more than just the bounding boxes. And as you can see, having this, we can also easily get the bounding boxes. So these are the trade-offs that one needs to be making if they are designing an autonomous driving car. All right, so you now saw that we have several different algorithms using just the cameras that can detect pretty much everything. So we should be good, right? We should be able to detect everything, or basically are cameras enough? So there are a few, or basically one major self-driving car company that they are just trusting the cameras and cheap sensors like radar. But several other companies, as I mentioned before, are also entrusting their vision in LiDARs too. So if the cost is nothing, then we should be using all the sensors that we want to, right? So why cameras are not enough? Because basically cameras don't work in low visibility conditions, such as rain, fog, or nighttime. And even then, even if it's just the morning and it is bright and shiny out there, it might not work. Like imagine that the sun is shining directly into the camera. The camera is basically blind, right? So cameras have their limitation. And you might say that, well, humans are using their eyes, so why cameras are limited? Because remember, in addition to the eyes that we're using, we're also using several years of experience. So we're not just relying on our eyes, we're relying on our perception. Like we're driving in a highway and we hear an emergency vehicle emerging, right? We don't see it, but we know it's coming from somewhere. So we're alert. And as soon as we see something, we go somewhere, right? So these are the things that we've been trained over the years. And these are the things that the car doesn't have. Car is just using the cameras. So probably because this is an application that it's very, very important. And also if we don't do a good job, human lives are in danger. We need to pad it with other sensors if the budget allows. All right, so we saw before that we had other sensors such as radars. As I said, radars are currently being used in many cars, and if your car does have a backup camera and backup sensors, whenever you're backing up, it's beeping. These are all the radars. Or if your car has a collision control, these are radars. And these are cheap, so you can put it all around the car. But how does a radar work? Radar works basically by transmitting a radio wave in pulses, and after the wave hits the object and comes back, using the Doppler effect, we can detect the speed and location of the object. They are cheap, so they can be everywhere on the car, which is very good. But the downside is that they are very low res. Basically, in a distance of 100 meters, the radar resolution is several meters, and it might happen that it actually misses a car that is in front of them. And why 100 meters, you say? Imagine you're driving in a highway with a speed of 65 miles per hour, right? 100 meters is nothing. You need to see that. And because of this low res, you can't really distinguish between the type of vehicles. You can just say this is something that's going with this speed. That's about it that you can talk about it. But they are cheap and useful. What else we can use? We can use LiDARs. LiDARs are really good. They are a sensor that have a very high resolution, and the standard LiDAR resolution is few centimeters at 100 meters. Basically, we can see everything, and it gives you a cloud point that has all the objects in it. It works very well in low light conditions and is able to create a detailed 3D map from around you. And basically, the car companies are using it for that. Basically, LiDAR works by emitting lasers at incredibly fast speed. And similar to radar, when it gets back, we can detect what's around us. The con, however, is that it's very, very expensive. And very few, if any, can be placed on the car. And that's why some of the car companies are going without LiDAR, because for commercial use cases, having, for example, $100,000 sensor doesn't make any sense. It's more expensive than the car itself, right? So that's why we have to think it through where we want to put it. And that's why there are several companies that are offering LiDAR-based solutions that are cheaper. But having all these sensors, is that enough? Probably not. So a lot of the car companies who are working in self-driving industry, they also have HD maps. So whenever we're driving to somewhere unknown, a lot of us will make mistakes, right? So having these HD maps ahead of time help a lot with the car. We need to know which lane we need to be if we are going somewhere. And if there's any construction, building, what is around us. So these are the HD maps that usually the car companies build ahead of time and feed it into the car. But these needs to get updated. Like imagine that you have a construction site, right? It needs to get updated to know that we're not going there anymore. All right, so these were the basics of a self-driving car. I talked about several different algorithms, and you can go to all like the major conferences or journals and find all the deep learning or non-deep learning based solutions for all of this. And it seems like solved, right? No, I mean, we don't see self-driving cars today on the cars. We've seen it as a test module, but not yet commercialized yet, because there's so much more than just these sensors. You need to fuse them together. You need to take the accuracy much higher because human lives are in danger. But this was just the basic of knowing how, if you were to do self-driving, what are all the different components that you might need. Okay, so this was the first part of my talk. The second part is about visual search. So what is visual search? Visual search is basically search, but using the image domain. So here is an example that I took from Adobe Stock. Basically, what you do, you search for something, you like an image, and then you want to find similar images. In Adobe Stock, we have implemented several different meaning of similar. So you can say similar in content, and this is similar in content. You can find similar just in color, and it can be other kind of content, right? Or it can be similar in all of the above, which the last one shows you. So basically, visual search is search in the image domain. So the previous example was just using finding similar using content, color, and composition. But now in Adobe, we took it even one step further. What if I want to make sure the size of the object that I'm looking for in the image is the same? Or it's positioned in somewhere that I like it to be, like the Eiffel Tower. I want to be in the right side of the picture, not in the middle of the picture, right? So this is also an application of visual search that we deployed in Adobe. But what else? It is very useful in e-commerce. This image is taken from Amazon, and this is the product that we launched while I was in Amazon. This is called Style Snap. And then basically you take a picture of something you like. You see it, for example, in somebody's home, and you really like this fan, right? Or this lamp, sorry. And then you want to buy it in Amazon or somewhere else, right? So what it does, you upload the image that you like. Internally, it does object detection, similar to what we talked about in autonomous driving. Then it makes the objects that it detects into a bunch of features. Now having these features is very easy. We map everything else as well, and then we now do a nearest neighborhood search and find the results. So visual search has a lot of applications in e-commerce. And this is why I mentioned you can use computer vision in fashion. Imagine that you have a picture of an influencer that you like. You really, really like the clothing or outfit that they're wearing, but you don't know where they got it from. So all you do is you take a picture from them, you upload it, you get the objects, and then voila, you get the similar clothing that they're wearing. So computer vision can be very useful in a lot of places. All right. So here we talked about we need to do object detection first. This is one example of an object detection algorithm. This algorithm is called YOLO. You only look once. And when it was introduced, it was very popular because it is super fast compared to all other. It was super fast when it was introduced compared to all the other object detection algorithms were based on deep learning. So basically, you look at the image, you do several different bounding boxes, and then you find the ones that you're looking for. And this is the network architecture of the YOLO paper. Now that you have the object detected, you need to know if you need to find the similar objects. In order to do that, we train something called a triplet loss network. Basically, what a triplet loss network does is get an image as an anchor, get a positive sample. A positive sample means a sample that looks like the anchor, and gets a negative sample. So what the network, what the network is trying to do is trying to minimize the distance in the feature space between the images of the same person and maximizes the distance between the images of the people who are not the same. Right, so we feed all these 3 images into the network, and then the network says these 2 images are close and these 2 images are far. And at the end of the day, by training this network, we will have a feature representation of the image. And the feature representation is what we need to do the KNN search. So now that we encode the image into features, if we encode all of the images that we have into the features, it'll become something like this, where you can see, like, for example, tops are these green ones. Dresses are these purple ones, and so on and so forth. So basically now when a new image comes in, you do the object detect, and now you realize this is a top. You do the you put it through the triplet loss network, you get the features, and now you can easily see, oh, okay, this is the top, somewhere around this is the top that I'm looking for. So this all sounds very easy, right? You only needed few modules compared to autonomous driving. And that's true. It's much, much, much easier compared to autonomous driving. Nobody cares if you buy the wrong shirt, right? But it's not as easy as it looks either. Why? So imagine that you have a query image, which is this dress. Which one of these you call closer? This is a red dress, but this one is the exact same dress in black. Which one do you call closer or similar? Like if I show you this result, would you be happy? Or if I show you this result, would you be happy? That all depends on what you call similarity, right? So this is a problem, very subjective. I can train a similarity network of what I call similar. So basically it depends on the product design. One way that we went around it is define similarity scores. So basically, sorry if you're hearing a toddler. So basically, if we have the object, we can define what similar means to us. So basically, if they're the same object, it is more important. So basically, here are the things that I listed. If they're the same objects, if they are the same color, if they're the same orientation, if I have the same feature. For example, for this dress, this has a sequin, this is long, it has a certain neckline, or is sleeveless, right? So all of these features matter. So all I have to do when I define similarity is to come up with metrics that matters to my product to define similar objects. So when I can definitely evaluate the objects, but that certainly is easier than autonomous driving. All right, so here was 2 major applications of computer vision in industry, and these are the applications that are currently heavily being used in industry. And there are several autonomous driving industries, there are several e-commerce companies that are using visual search. So all these very advanced AI features are currently being used. So in the last 2 minutes of my talk, I want to talk about ethical AI. Remember, the reason that we're doing AI is because we want to make sure that people's lives are better, right? But we have to be very, very cautious of what algorithms we are building. So the objective for all AI applications should be, it has to be beneficial. It has to avoid unfair biases. It has to incorporate privacy. We don't want to give all of our stuff to some algorithm engineer to come up with the design, right? But there are challenges. The biases in AI system. Imagine that you train a person detector that is only trained on certain people of color, right? Then you can detect other people. And in a system like autonomous driving, this is dangerous. This means that you might not detect a human in front of you and then eventually hit them, right? The other thing is that you want to make sure that it's not getting weaponized, the artificial intelligence. Like a few years ago, there were some papers that were trying to detect who will become a criminal based on just their face. This is unethical. Like, you cannot decide somebody is a criminal based on their face, right? So these things matter a lot. And more companies these days are making sure that any AI application that people are building, it actually is beneficial and is not hurting the humanity. So I just wanted to mention that please take AI ethics very seriously and keep thinking about that while designing an AI system. All right, with that, I'd like to conclude my talk. Thank you very much.
Wow, thank you, Shana. That was amazing. And I know this virtual audience is giving you a huge virtual round of applause.
Thank you.
Thank you. We appreciate you sharing with us today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.